Hello friends, welcome to APM Stats Connect. Today in this video, we will discuss about an important family of distribution called Pitman family. Before going to the definition, we will have some common assumptions that let x1, x2, etc. xn be a random sample of size n from the class f of x comma theta. Theta belongs to omega subset of R1. Here f of x comma theta, it denotes the probability density function of a random variable, and theta, it is the parameter, and omega is the parameter space, which is the collection of all values that theta can assume, is again a subset of the real numbers, where the range s theta equal to z x such that f of x comma theta greater than 0 depends on theta. A common characteristic of Pitman family members is that the range, that is the collection of all values of x such that the PDF f of x comma theta greater than 0 will depends on theta. So here we can see that the prime example of such family are uniform 0 theta, that is uniform distribution over 0 theta. Here the range of x, it lies between 0 and theta, and clearly it depends on the parameter theta, 0 less than x less than theta. Another example is exponential distribution with the location theta, that is the PDF will be of the form exp of minus of x minus theta for x greater than theta. We have the form of PDF of uniform 0 theta. The PDF of uniform 0 theta has the form f of x comma theta equal to 1 by theta, where 0 less than x less than theta. Here the upper limit depends on theta, whereas for exponential distribution with the location theta, that is for an exponential distribution with the probability density function f of x comma theta equal to e power minus x divided by e power minus theta, theta less than x less than infinity, the lower limit depends on theta. And in both the case, the PDF have the form u of x by v of theta over s theta. So this is again a common form of the probability density function for the members of Pitman family. The definition is, let the set f of x comma theta, theta belongs to omega subset of R, be a family of PDF such that f of x comma theta equal to u of x by v of theta for a of theta less than x less than b theta, where a of theta less than b of theta for every theta belongs to omega, and omega is an interval. Then the collection f of x comma theta, theta belongs to omega subset of R1 is a Pitman family. Every distribution belonging to Pitman family will contain common properties, and in this video we will discuss mainly about how to find the minimal sufficient statistic for the members of Pitman family. In the first case 1, we are considering the case where the lower limit a of theta is a constant. For example, 0 less than x less than theta, uniform distribution over 0 theta, the lower limit is a constant 0. In that case, the minimal sufficient statistic will be the maximum order statistic xn. When the upper limit b of theta is a constant, then the minimum order statistic will be the minimal sufficient statistic for the parameter theta. Here we have the likelihood function. We already said that the PDF of Pitman family members can be expressed as a ratio of a function of x divided by function of theta. So the likelihood function will be of the form 1 by u of v theta, 1 by v of theta power n into product I equal to 1 to n u of xi, a less than xi less than b theta. This is the condition when the lower limit is a constant, a of theta equal to a. Okay, and we will add this condition, this condition into the joint density using a function which is given by phi of c comma d equal to 1 if c greater than d and 0 otherwise. So we can express a less than xi by psi of xi comma a. Whenever xi greater than a, this function will equal to 1 and 0 otherwise. Similarly, psi of b theta comma xi, whenever b theta greater than xi, psi of b theta comma xi equal to 1 and is 0 otherwise. You can see the remaining steps, and here we are finding the minimal sufficient statistic using likelihood equivalence, and finally we can see that the minimal sufficient statistic is equal to the maximum order statistic xn. The maximum order statistic or the nth order statistic xn is the minimal sufficient statistic for theta when the lower limit a of theta is a constant. Similar way, we can also prove the condition where the upper limit b of theta is a constant and a theta is a function of theta. Writing the same conditions, considering the likelihood function, and also we add this condition using the function psi which is defined as above, and solving we get the minimum order statistic or the first order statistic is minimal sufficient for the parameter theta. We will also consider when a of theta and b of theta depends on theta. Okay, so first we consider the case when a of theta decreases and b of theta increases. Like minus theta comma theta, considering a uniform distribution over minus theta theta, as theta increases a of theta decreases and b of theta increases. So in such situation, how we can find the minimal sufficient statistic for theta? The minimal sufficient is given by t of x is equal to maximum of a inverse of x1 comma b inverse of xn. Okay, so if we are considering u, that is uniform distribution over minus theta comma theta, and the question is to find the minimal sufficient statistic for theta. Here a of theta equal to minus theta, b of theta equal to theta. Okay, so a inverse of x1 it will be minus x1 and b inverse of x1 will be xn. Then the fourth case is when a theta increases and b theta decreases with theta. In that situation, the minimal sufficient statistic capital T is equal to the minimum of a inverse of x1 comma b inverse of xn. So here in this video we have discussed four situations where the lower limit a of theta is a constant and b theta depends on theta. In such situation, our minimal sufficient statistic is given by the maximum order statistic xn. Here you can see the result A. Here we have the result A, where the lower limit is a constant and upper limit b theta depends on theta. In such situation, the minimal sufficient statistic is given by the maximum order statistic xn. The second case is when the upper limit b of theta is a constant and lower limit a of theta depends on theta. In such situation, the minimal sufficient statistic for theta is given by the minimum order statistic x1. The third condition is both the lower limit and upper limit depends on theta, and again we can divide that into two, like a theta decreases and b theta increases with the theta, and the second one is a theta increases and b theta decreases with the theta. When a theta decreases and b theta increases, the minimal sufficient statistic is given by t of x is equal to maximum of a inverse of x1 comma b inverse of xn. And the second case, that is when the lower limit a theta increases and the upper limit b theta decreases with theta, then in that case the minimal sufficient is t equal to the minimum of a inverse of x1 comma b inverse of xn. Now let us discuss different examples. Consider this example 2.6.1. Where the density function is f of x comma theta equal to 1 by 2 theta minus theta less than x less than theta, and the support s theta is equal to minus theta comma theta. So it depends on theta, and as theta increases, the lower limit a theta decreases and b theta increases. So we have, in this situation, the minimal sufficient statistic is given by maximum of A inverse of x1 comma B inverse of xn. Okay, so here A of theta is minus theta and B of theta is theta. Then A inverse of x1 will be equal to minus x1 and B inverse of xn is equal to xn. Then the minimal sufficient statistic will be, using the above result, we have capital T equal to the maximum of minus of x1, that is minus x1 comma xn, is the minimal sufficient statistic for theta. Or x1 comma xn is also minimal sufficient for theta. In the next example, you can see x1 comma x2 are IID from uniform theta comma theta plus 1. This is an important result, and here you can see both the lower limit and upper limit increases. So here they had the density function for uniform theta comma theta plus 1 will be 1. So the likelihood function is again equal to 1 with the theta less than xi less than theta plus 1, where I equal to 1 comma 2. And here they say that if x1 comma x2 is the order statistic which is sufficient for theta, in view of the general result for samples on continuous random variable, we have g naught of x1 comma x2 of theta. This is the result of order statistic. Their joint density is equal to 2 factorial into theta less than x1 less than x2 less than theta plus 1. Which is equal to 2 factorial into psi of x1 comma theta into psi of theta comma x2 minus 1, where psi is defined as the above example. And using the likelihood equivalence, we can see that the x1 comma x2 is the minimal sufficient statistic for the parameter theta. The reference used in this video is a first course on parametric inference by B.K. Kale. For those who need these steps can refer a first course on parametric inference by B.K. Kale. And thank you for watching. You can post your suggestions on the comment box. And once again, thank you.